In our acid-base reactions, we saw that we would produce a salt, and salt is a generic way to say ionic compound. How do we know if that ionic compound is going to be soluble or insoluble, if it's going to be aqueous? Well, we need some rules or a way to predict whether those compounds dissolve in water or not. If it dissolves, we say that it is soluble. And in our chemical reaction, we label soluble compounds AQ. If it doesn't dissolve when it's added to water, we say it's insoluble, and we label it S. And I know this can be confusing, but the S stands for solid. So if it doesn't dissolve, it remains as a solid in the solution. Sometimes the best way to determine whether or not a compound will dissolve in water or not is just to try. Do some experiments, see whether or not it dissolves, and then figure out some rules based on those results. We call this particular way of doing experiments the empirical method. Try it out, see what happens, and figure out the rules once you have your observations. It's my favorite way of doing chemical reactions or chemical experiments. Based on those experiments, we have a list of rules, and we call them solubility rules, for compounds that are generally soluble in water. So if they are in group 1, group 1A, or the first column of the periodic table, they are always soluble no matter what, and there are no exceptions. So the right side of our table are the exceptions to the rules. So if it falls in this column, that means that it will be insoluble. If we have nitrate containing compounds or acetate containing compounds, they are always soluble no matter what. Most chloride, bromide, and iodide compounds are soluble unless they are attached to the cations of silver, mercury 1, or lead 2. Most sulfate containing compounds are soluble unless it's silver 1, calcium, strontium, barium, or lead 2. We also have some rules for insoluble compounds. So insoluble compounds, so the anions on the left are generally insoluble unless they are an exception. So notice our exceptions. Our exceptions are those group 1A compounds for all of our anions. We do also have, for hydroxide, we have some that are slightly soluble, which means that they are mostly insoluble. So a little bit will dissolve, but most of it will stay as the solid. So for our hydroxide, it's mostly insoluble unless it's attached to anything on the right-hand side. Our sulfides are insoluble unless it's attached to the group 1A, which are always soluble. Carbonates and phosphates are usually insoluble unless it's attached to the group 1A compounds. So here's some practice. Use those solubility rules to figure out if the following compounds are soluble in water. Potassium hydroxide is soluble because it contains potassium. Potassium is group 1 metal, and so it is always soluble. Our silver bromide. Bromides are usually soluble, but silver is one of the exceptions, which makes this an insoluble compound. So we would label it as a solid. Our potassium hydroxide would be AQ. Calcium chloride is soluble. Most chlorides are soluble. Calcium is not one of the exceptions. So this would be aqueous. Lead nitrate. Well, nitrates, no matter what they're attached to, are always soluble. So lead nitrate is no exception. So this would be soluble, labeled AQ. Lead sulfide. Sulfates are usually soluble, but lead is an exception. So this would be insoluble and would be a solid. Precipitation reactions use these solubility rules to predict whether or not a solid forms upon mixing two aqueous solutions. So we take two solutions, we add them together, and sometimes we get an insoluble product that is called a precipitate. So the solid forms in the solution. Here's an example. So if we take lead or potassium iodide and add it to lead nitrate, our products we determine by taking the cation and combining with the anion. We get potassium nitrate. Potassium compounds and nitrate compounds are always soluble. We take the lead, combine it with the iodide. Iodide compounds are usually soluble, but lead is an exception, so we end up with a solid. And so in this particular example, we take two clear colorless solutions, and when we add them together, we get a fluorescent yellow solid. It's kind of an impressive reaction. If we think about what's going on in the net ionic equation, we've got potassium ions and iodide ions in one solution. We've got lead ions and nitrate ions in the other. And when they combine, our potassium and nitrate are going to be our spectator ions, but the lead iodide is going to be our insoluble product that has strong enough interactions that it overcomes the forces of the water holding it in solution and falls to the bottom as a solid. So our net ionic equation in this case would be Pb 2 plus 2I minus gives us our lead iodide solid. We can have the case where no precipitate forms. If both of the products of the chemical reaction are aqueous, it means that everything remains as the ions and no reaction occurs. So if we start with potassium iodide in solution and we have sodium chloride in solution, because the potassium chloride and sodium iodide are both aqueous, they're both soluble, that means that all of the ions will just be a mixture in the solution and there will be no reaction. So let's try an example. So we've got an aqueous solution of potassium carbonate and an aqueous solution of nickel 2 chloride. So potassium +1 charge off of the periodic table. Our carbonate is a -2 charge. All right, nickel 2, so it tells us that nickel is a +2, chloride based on its position is a -1. So it's going to take 2 potassium to balance the charge of the carbonate. It's going to take 2 chloride to balance the charge of the nickel. To determine what our products are, we're going to take the cation of one, combine it with the anion of the other. So potassium is a +1, chloride is a -1. We use the charges to determine what the compound is. So our compound has to be neutral. 1 potassium, 1 chloride. So we end up with KCl. Nickel is a 2+, carbonate is a 2-, so we just need one of each to balance the charge. Now we can go and balance the chemical reaction by changing the coefficients. So nickel, we have one, carbonate, we have one on each side, so that's already balanced. If we look at the potassium and the chloride, there are 2 on the left side, only 1 on the right. So we need a 2 in front of our potassium chloride. Now we check our solubility rules. So potassium-containing compounds are always soluble no matter what. So that's going to be AQ, aqueous. Nickel carbonate, carbonates are usually insoluble. Nickel is not an exception. So this will form a solid. So we do have a reaction where we form nickel carbonate solid in this chemical reaction. Here's one for you to practice. See if you can, or two to practice. Determine what the products are and balance the reaction. If we look at potassium chloride and silver nitrate, we're going to swap cation with anion. They are all +1 and -1, so it's just going to take one of each. Now we have to look at our solubilities. So potassium and nitrate, no matter what they're attached to, are always soluble. So that will be a soluble product. Silver chloride, chlorides are usually soluble, but silver is an exception. And so we would get a silver chloride solid. If we look at sodium sulfide and calcium chloride, we're going to take the sodium, combine it with the chloride, calcium with the sulfide, and we produce +1, -1, so we get sodium chloride. Calcium's a +2, sulfide's a -2, so we get calcium sulfide, no subscripts required. To balance the reaction, we're going to need 2 of the sodium chloride. If we check our solubility rules, sodium-containing compounds are always soluble no matter what. So our sodium chloride is soluble. Our calcium sulfide is going to be a solid. We also have the case when we exchange ions to make our products that we can form gases. So one example of that would be in our first chemical reaction. When we exchange our ions, we end up with dihydrogen monosulfide, which is a gas. And so we would see bubbles coming from our chemical reaction. How do we know it's a gas evolving reaction? Well, we have gas as a product in the chemical reaction. Sometimes it's not a direct process to get to our gas. Sometimes we have a decomposition of one of the products. So in this case, we have sulfurous acid that is formed, and that decomposes into water and sulfur dioxide, which is a gas. And so that gas is our product. This particular reaction can be used to identify the presence of carbonate in stones. By adding acid to a stone, you can see if there is calcium carbonate or limestone present, because you'll see the carbon dioxide gas given off by the chemical reaction.